just start with a brief introduction and allowing other people to connect. Hello, everyone. It's a pleasure to be here. This will be our last appointment of the GGI Tea Breaks series before the summer break, but we will start again in September. We have not decided yet, but stay tuned on our webpage because we want to continue this experience, which in my opinion has been very, very positive. It's a pleasure to have as our last speaker for this first session, Gia Dvali, and I would like to thank him very much to accept to give his viewpoint, and let me invite Roberto to introduce him.
Okay, so thanks, Stefania. So welcome again to everybody. Let me introduce very quickly Gia Dvali. So he is a professor at Ludwig-Maximilians University and a director at the Max Planck Institute for Physics in Munich, where he is now. He got his PhD in Tbilisi University in Georgia, and then he made research at ICTP in Trieste, Pisa University, CERN, and NYU. If I have to describe his research, certainly he has been working on beyond the standard model and is interested in studying the fundamental laws of physics. He, of course, is well known for his study, his work on extra dimensions, especially his papers on large extra dimensions together with Nimar Kenemed and Savas Dimopoulos. And then he went on in his study of gravity, and more recently he studied black hole physics and became interested also in because of this study on black holes. He became interested in quantum info and also on many body quantum systems, and he has developed a very original approach to the physics of black holes. So today he will give us his viewpoint on naturalness and the hierarchy problem. And so please, I leave the stage to him.
Thank you very much. I would like to thank organizers and thank you for the introduction. It's a great pleasure to be here to give this talk. And I'm going to share, I assume you can hear me okay? And I'm going to share some ideas about de Sitter and naturalness. And so here are some notations, pretty obvious. These are pretty obvious. So, you know, like I will work in usual units.
Sorry, Gia, I forgot to say that unless there are very urgent questions, we will have questions at the end. So sorry,
yeah, that's better. Yeah, I agree. Yeah, it's better to have questions at the end. Yes.
Okay.
And also, please, you can write in the chat. Yeah. Of course. So so these are notations pretty obvious. So Newton's constant is G, Planck scale is MP, Planck length is LP, cosmological constant is Lambda, and de Sitter curvature radius, Hubble radius is R. Okay. Now de Sitter is an extremely important space-time and also very well known. So here I'm writing in the interval in de Sitter space in familiar slicing. So A is the scale factor, which expands exponentially with cosmic time t, and R is the curvature radius of de Sitter, or Hubble radius, which is constant in time. Classically, it's constant in time. Now the curvature radius, of course, is related with the source, which I call lambda here. And the source is pretty unusual, as we know, because it has a negative pressure. Okay, and that kind of source is impossible to produce by ordinary stuff, by putting together like matter or radiation. And so if the interpretation of this source is in terms of vacuum energy. So if vacuum had energy, it would look like a cosmological constant, lambda. Okay, so it's introduced by Einstein, by the way. So now, semi-classically, I mean, most of the work on de Sitter was done semi-classically. Semi-classically means we fixed geometry as being rigid and God-given, and then we consider quantum fluctuations on top of this geometry. And so in this limit, de Sitter is pretty well understood. And so, for example, we know that an observer, so here's the observer, Alice. Observer is surrounded by a horizon. And also there is a radiation, so-called Gibbons-Hawking radiation, with temperature inverse of the size of the curvature radius, pretty similar to Hawking radiation from black holes. And there is also an entropy, so-called Gibbons-Hawking entropy, which is again pretty similar to entropy of a black hole because it scales like area of the horizon area in Planck units. Okay. So de Sitter-like states, they play a very important role in general in particle physics and in cosmology. Why? Because first, according to the inflationary paradigm, we come from de Sitter. Okay, so our early universe was in some kind of de Sitter-like state. Of course, not real de Sitter, but de Sitter-like state, temporary. And observations indicate that we are also re-entering in de Sitter, like something like de Sitter, again, de Sitter-like state. So here's a question mark, and I will discuss this question mark later, okay? Now, the story, this story with cosmological constant and de Sitter is accompanied with a puzzle, okay? We call it, sometimes call it cosmological constant puzzle, okay? Very naively, you can phrase it as why is lambda so small, much smaller than Planck density. But the main source of the puzzle is the following, okay? Once you try to interpret lambda in terms of particle physics or quantum field theory, you discover immediately that it's ultraviolet sensitive. It's extremely sensitive to the cutoff of the theory, ultraviolet cutoff of the theory. Okay, so therefore, if we naively estimate quantum corrections to lambda, not compute, because nobody has computed those corrections precisely because they are ultraviolet sensitive. So, except in like trivial cases, like exact supersymmetry or something like that. So, if we naively estimate these corrections, we'll discover that again they are highly sensitive to the cutoff of the theory. So, MUV is the cutoff of the theory, and any sensible cutoff that you can put from standard model, okay, would give a very enormously large value for lambda, which would have to do nothing with what are the observational bounds, okay? So therefore, it looks unnatural that lambda is small. And that's why this is usually viewed as a so-called naturalness problem, okay? So naturalness puzzle, it's not really a problem, it's a puzzle, okay? Now, in this prism of naturalness, there were a lot of efforts to try to understand, to offer an explanation, a dynamical explanation of why is this happening, okay? And I mean, there are many, enormous number of different proposals and different ideas. I also tried to contribute into that. Some of the ideas are really highly imaginative and really fascinating. However, I think there is a common consensus that nothing really works in a satisfactory way. At least I'm not aware of any working proposal, a solution for this. However, there is a side of the story which led to a temporary settlement, okay? And I will discuss this settlement a little bit later, okay? Okay, so the question now that I want to address in this talk, what is, if we put aside issues of naturalness and for a moment ask whether the question should be different, whether instead of naturalness, we should be thinking about consistency. Okay, what does quantum gravity has to say about lambda? Okay, and so I will follow a personal path, how I came to the understanding that I have today. Okay, so in 90s, okay, I was trying to understand together with collaborators, the different collaborators, we were trying to understand how to realize the Sitter-like state, mainly motivated by inflation, obviously. How to realize the Sitter-like state in supergravity and then in string theory. Okay, and so so in string theory, this is the question we asked Henry Tai and myself: how to realize the Sitter-like state in string theory. Now, as I said, in order to realize the Sitter-like state, we need a source that has energy momentum tensor, which is similar to lambda, to cosmological constant. So energy momentum tensor with a negative pressure, okay? And actually, string theory offers such a source. And so we came up with this idea of what is called D-brane uplifting, okay? So what is the idea? Now, as you know, in string theory, elementary entities are strings, okay? And the different vibrations of the strings, they are different particles. So the different elementary particles, they correspond to different harmonics of string vibrations. And the strings can be open and closed or closed. And so vibrations of the closed strings, they give lowest vibrations of closed strings, they give gravity. Okay, they incorporate gravity. And that's very nice. That's why string theory was recognized immediately that this must be a theory of quantum gravity, because in low energy spectrum, it contains graviton. Okay. There are also open strings. And then it was realized that string theory also contains, at least in some descriptions, it contains these very interesting objects called D-branes. So was this introduced by Polchinski, made really very concrete by Polchinski. So these D-branes are extended objects, okay, like solitons. And they have this property that the open strings, they end on them, okay? So directly boundary conditions. So that's why they're called D-branes. Now the D-branes, they have word volume. Okay. So if you are an observer that lives on this word volume, it sees certain spectrum of open strings, of open string vibrations. D-branes can also be connected by strings. Okay. And the word volume dimensionality can be different. Okay, of course, we are here interested in the D-branes whose word volume dimensionality is larger than 4 or larger, because we want to precisely come up with the source, cosmological constant like source. And indeed, D-branes, they have this property that their energy momentum tensor is very similar to cosmological constant because it has negative pressure. Okay, but they have tension. And they have negative pressure. Also, they have this property that the word volume is boost invariant along the word volume coordinates. And so the transverse coordinates are just perpendicular to the branes. And so we thought that this was ready-made for incorporating the Sitter in string theory. It was very nice. Now, the thing is that it's not so easy, actually, because the isolated D-brane is known to be a straight isolated D-brane, is known to be a so-called BPS state. Basically, this means that it preserves part of the supersymmetry, okay? And because of this, it cannot create the Sitter. So what happens is that the D-brane has tension, which gravitates, but it also has an electric type field, a flux, Ramon flux. And so they two compensate each other. So the metric is not the Sitter in that case. So in order to produce the Sitter, what you have to do, you have to produce a non-BPS configuration of D-branes, okay? So for example, and let it go. So this was our idea. So you produce some non-BPS configuration of D-branes, which has excess of tension over the other parameters, like for instance, total charge. Okay, for example, if you have D-brane and anti-D-brane, the total charge is 0, but tension is there. And so then you let it go. Okay, and while the system tries to settle down to a vacuum, whatever is the true vacuum, meanwhile it can produce some de Sitter-like state. So this was the idea. Okay, and so indeed we can realize this idea. And so, for example, simplest was this realization in terms of brane and anti-brane. Okay, D-branes, stack of D-branes and anti-D-branes. If you displace them away from each other, they attract each other because they have attract gravitational. They also attract through the charges. And so if you displace them and then let them go, this is the picture. So an observer on the world volume sees something like de Sitter. Okay, something like world volume de Sitter. So world volume, I mean like 3 + 1 dimensional de Sitter temporarily, while these D-branes fall towards each other. So this was sort of this brane walled realization of inflation, where two brane walls, they fall towards each other. Finally, some subset of branes and anti-branes annihilates, and this rehits the universe, okay? And this is the beginning of the hot Big Bang. And indeed, I mean, it looks very elegant, this idea. So it looks like the string theory just offers for free almost infinite number of possibilities to produce a de Sitter-like state, okay? And we continue to work on this and try to take it to the extreme. In other words, trying to understand, I mean, how long can such a de Sitter-like state can last, okay? So for example, can it give eternal inflation? Can it be an eternal inflating thing? Or some temporary stabilization? And so with my experience, it never worked. And always there was a good reason why this doesn't work. And now you see, this is very important to understand. Here we are dealing with a situation when Henry and I we wrote this idea, we came up with certain assumptions, of course. So there was set of assumptions that has to be satisfied in order to get this picture working. Okay, so this is de Sitter. For example, that the volume of extra dimensions must be stabilized and should not be disturbed by this motion of the branes, okay, and so on. And these assumptions, they look pretty natural, okay? And therefore, it looks natural that the possibilities to produce the de Sitter-like state in string theory should be almost unlimited, okay? But every time we would have some working example that would be possible to trace within a calculability domain. Within calculability means that no strong coupling, so the theory is weakly coupled, no coupling should become strong, neither string coupling nor some type of Toft coupling, okay, and so on, okay. I mean, it never worked. So usually the number of inflationary Hubble times, like in number of inflationary E-foldings, was on the borderline, okay? Always the system wanted to get rid of this de Sitter-like state as soon as possible, okay? So this was my experience with all this struggle with this type of constructions, okay? Now, of course, there were other people try to do, as you know, probably that there is enormous literature on offering different types of constructions of de Sitter type states. And so, of course, very, very often what is happening is that we make assumptions, and these assumptions look natural. And so you cannot really imagine why they should go wrong. But at the end of the day, when you dig it deep, you see that there is always some story whenever it's calculable theory tells you that this de Sitter is unstable. It's not really de Sitter because it's unstable. It runs away or relaxes very fast. Okay. So I think there is a good reason for that. Actually, if you follow these technicalities, of course, I will not enter in this talk in that. Technicalities are really very extremely interesting, and this is really very interesting from the point of view of effective field theory and effective supergravity. How to match why string theory doesn't want to give de Sitter with the effective supergravity understanding. For example, the supersymmetry breaking is of so-called D-term type breaking. which is intertwined with existence of so-called Phi-Leopolus terms in superior, and so on, okay? So it's a beautiful story. But what I want to, I'm looking for a more fundamental reason in this talk, okay, for why this doesn't work, all right? So before going there, of course, this has an impact. This is very important to settle down this question, because it also affects our understanding of naturalness in general. Because, so very often the assumed picture is that, and it looks, again, I'm saying this looks natural, because naively it's very hard to imagine why this shouldn't work, because the string theory contains so many tools, like in form of D-branes, for creating different configurations with energy, positive energy, positive effective, positive potential energy, that it looks, naively it looks unbelievable. How can there not be an almost infinite number of possibilities to stabilize this de Sitter vacua, okay? And indeed, I mean, the assumption is very natural. So therefore, we sort of often assume that, okay, this must be the case. And therefore, it looks very natural that string theory offers a huge number of de Sitter vacua. So this is called de Sitter landscape on string theory. Now the story of de Sitter, so this is very pictorial here, okay? And so very densely populated landscape of de Sitter vacua. Now, of course, the story of de Sitter landscape, this goes before string theory. People like Abbott and Teitelboim and others, yeah, they were considering this type of picture within effective field theory. So sometimes it's called, this type of potentials are called washboard potentials, okay? And so on. But string theory made it very, seemed to make it very explicit, okay? This was the source for this. And then the conclusion from here, sometime in certain approach was drawn, that this can replace naturalness, okay? So we can replace naturalness by selections on the landscape, such as, for example, anthropic selection, okay? Now, the anthropic principle itself, and probably everybody here is familiar with this anthropic principle. Basically, what the anthropic principle does, it correlates value of parameters with the environment that these parameters create, and the possibility of an observer to exist in that environment, okay? So if observer is asking the question, why is parameter what it is, the anthropic principle could answer that if it works, in that case. It doesn't work always, but if it works, it can answer, okay, this is because this parameter is necessary for the environment in which a given observer can exist, okay? So this goes back to Carter and Carr and Rees and Barrow and Tipler and others. But Weinberg made it very scientific for lambda, because he showed that he gave an argument that small lambda is required for formation of galaxies. Of course, correspondingly, it's required for everything else, because we cannot exist without galaxies and structures. Okay, now, this is not sufficient, however, okay? Because if I simply tell you, okay, there's a parameter that, and this is incompatible with your existence, that doesn't really explain it in a scientific way. You need to have a certain engine, a mechanism for actualization of different values of these parameters, okay? And this actualization mechanism is eternal inflation on de Sitter landscape. And this was made thanks to works by Vilenkin and Linde, again, precise. So inflation, for certain shapes of the landscape, inflation can last eternally. Why? Because here's the picture of a slow roll scalar field. Because for certain values of for certain slopes, the scalar field can go down, but it can also go up by quantum fluctuations. And so there is a regime in which inflation is eternal. Of course, if there is a local minimum, inflation is eternal. This was the case in the original proposal by Alan Guth, where he put forward this great idea of inflation. Okay, there, of course, inflation is eternal, and that was a problem for the proposal, which was then later solved by slow rolls, by Albrecht, Steinhardt, Linde, and others. Anyway, so this is the picture, right? So in the landscape. However, so of course, now the story with anthropic is controversial. And by no means I'm here to defend anthropic selection, actually, because it's irrelevant. For what I want to say is that situation is exactly the opposite, okay? And quantum gravity actually eliminates the de Sitter landscape. So there is no de Sitter landscape in quantum gravity. Now, throughout the talk, I will use string theory as a reference point. So often I will talk about string theory, but it's just a reference point because it's useful, because string theory makes things explicit. For example, like d-branes, okay? But whatever I will say will be valid for arbitrary theory of quantum gravity if it's formulated through the S matrix, okay? So basically what I want to argue in this situation is the opposite. And this is great news. This is not a problem for quantum gravity. Actually, it's the other way around. Because in this way, quantum gravity nullifies the cosmological constant puzzle. Actually, quantum gravity tells us that it was never a puzzle. And there is a parameter which quantum gravity very precisely predicts, and that's lambda equals 0 in our universe. Also, of course, this affects our thinking about naturalness. So we're back to naturalness. Okay, so now as I said, I will follow the story. So the story was, I don't know, we are thinking that because these explicit constructions, they have many question marks all the time. There must be a fundamental principle which is independent of the constructions, okay, particular constructions. So there is a fundamental principle in quantum gravity and string theory, which there must exist fundamental principle, which tells us why we can never produce any de Sitter type local minimum or a landscape. And this fundamental principle has nothing to do with the particularities of the construction. Of course, the reason why constructions do not work is because there is an underlying principle, obviously. But we wanted to look for the principle, okay? There must be something fundamental about impossibility to construct the de Sitter vacuum in string theory or quantum gravity. And so we came up with this principle, okay, with Cesar Gomez and myself in 2013, finally. And our message is that in quantum gravity, string theory, simply excludes the de Sitter vacua, both stable or metastable. Moreover, it excludes any type of de Sitter future eternity, and including eternal inflation. Okay, now, S matrix is fundamental in this. And so I will follow my relatively more recent paper in which I try to put everything in the perspective. And to close all the loopholes. But the original idea was, of course, original idea was there, and also the mechanism was there, which I will explain. Okay, so now what is S matrix? So we know very well what S matrix is. It's a scattering matrix which controls scattering. So we have a theory, interacting theory, and in this interacting theory we have initial states, some initial particles, okay, far apart in infinite past, t equals minus infinity. And then we have final states, different possible final states in infinite future. Now, the S matrix requires existence of an eternal clock, okay? So it must be a well-defined eternal clock. And a hypothetical eternal observer. So here is Alice. Okay, so now then the S matrix gives you certain rules how the initial and final states relate with each other. So it's a matrix. Now, in principle, I can simply come up with a book. Of course, S matrix must be unitary, etc. Obviously, is unitary. But I can, for example, come up with a book, a manual, in which I will simply tell you what are the elements of the S matrix. Of course, with the infinite number of elements. Or I give you rules how to compute them. That doesn't matter. So once you have this manual, you are done with the theory. That's my formulation of the theory. I simply take this manual and give it to you, and you have a theory. Okay, so now in string theory, this is the way string theory is formulated. In string theory, we don't have any other formulation. In quantum gravity in general, we don't have other formulation. So the S matrix is the formulation of the theory, and this is of fundamental importance. Now, in order to formulate the S matrix theory, we need to satisfy certain necessary conditions. okay? As I said already, we need some globally defined time. And of course, this was known, this is well known, that this is absent in classical de Sitter. But I think the reason why we never said, oh, look, since there is no global defined time de Sitter is out, so forget about it. Because of the following reason, because of the way of effective field theory thinking. And that thinking is related with another ingredient, the existence of an S-matrix vacuum. So another necessary condition is that the vacuum is an S-matrix vacuum, okay? Here's the point, what I mean, okay? Now, the effective field theory thinking sometimes leads us to, if it's not applied correctly, leads us to wrong conclusions, okay? And it's obvious that this is what happened with de Sitter. I don't know, it's obvious, okay, this is probably what happened with de Sitter. Now, naively you can think, you say, okay, look, suppose we live in de Sitter space, okay? So there is some Hubble patch radius, which is like, I don't know, 10 billion light years away, okay, or more. Now, okay, you tell me I cannot define S-matrix because there is this de Sitter radius somewhere there, but who cares? If I do experiment at LHC, I do experiment at 10 to the minus 17 centimeters, why should I worry about this Hubble radius, knowing that the effects will be minuscule from the corrections in infinite future, basically, right? So I apply S-matrix computations to processes at LHC and they work, okay? So obviously, therefore, S-matrix is not so important, okay, for defining a theory. There is something that we don't understand. Actually, this reasoning is wrong. And the reason is that it implicitly assumes that the limits commute. In other words, this is very important, so please stay with me. What I'm saying is this, right? If you know, someone told you, your friend came and told you, look, I have this theory, and this theory is well-defined, okay? Now, if you know that theory is well-defined, then in a well-defined theory, if there is a small parameter, okay, you can go ahead and do computations approximately. There is absolutely no problem. In other words, if someone tells you that the theory with the Hubble radius of 10 billion light years is well-defined, of course, then you can go ahead and use the ratio of time scales, for example, the scattering time at LHC divided by the Hubble time as an expansion parameter. And of course, you can trust all your computations and you can use S-matrix. But this is only true if limits commute. But if you don't know whether your theory is well-defined, you cannot do perturbative or approximate computations in a theory which is ill-defined, because that doesn't make any sense. This is what is happening with de Sitter, okay? So, and vacuum clearly illustrates what is the problem here. And so I want to just illustrate this point. So here's the point, right? So here, let's imagine that we live in our Hubble patch and we're doing some experiment at LHC, right? Okay, so we have some in states and we have some out states. We also need a S-matrix vacuum. Now, what's the property of the vacuum? And this is super important. Now, vacuum is a state that must be infinitely rigid. In other words, vacuum should not be able to recoil and absorb information during the scattering process. Because if vacuum recoils and absorbs information, we will never be able to establish a dictionary. Because every time I do experiment, it will happen, the person that is looking at out states has to know what happened with the vacuum. And that's an impossible task, unless you have yet another vacuum, which is a correct vacuum. Okay, so this is the crucial point, okay? Now, can we do this in de Sitter? Okay, so can de Sitter be a vacuum from the point of view of this S-matrix reasoning? And the answer is yes, it can be, but there is a unique limit in which de Sitter can be a rigid vacuum. Now, this limit is when I take a cosmological constant, lambda, to infinity, simultaneously I have to take Newton's constant to 0, and simultaneously I have to take Planck's scale obviously to infinity, which is the same thing, but keep de Sitter radius finite, because I want to keep de Sitter geometry intact, okay? So keep de Sitter radius finite. in this limit, the vacuum is rigid. Nothing happens to it, okay? De Sitter will not absorb any information, will not take away anything, will not absorb anything, will not emit anything. Information, will not emit information. Gibbons-Hawking, of course, is there as a background. However, in the same limit, what happens is that the graviton, the quantum gravity trivializes. Why? Because the graviton, quantum gravity is about quantum scattering of gravitons or closed strings. Graviton coupling, scattering of graviton scattering is controlled by, again, by Newton's constant. So it's Newton's constant divided by de Broglie wavelength of momentum transfer, or which is the same thing as momentum transfer divided by Planck scale squared, momentum transfer squared. So therefore, in the same limit in which de Sitter becomes a good S-matrix vacuum, S-matrix, gravitational S-matrix becomes trivial. Okay, so this is the key point. The same thing happens with, of course, string theory, because it's theory of quantum gravity, exactly tells you the same. As I said, in string theory, gravitons are coming from closed strings. And indeed, if suppose you assume that in string theory we established a good S-matrix vacuum, okay? This is de Sitter with lambda. And we take the limit, and again, of course, we immediately discover that in this unique limit, the string coupling, closed string coupling goes to 0. So the closed string S-matrix becomes trivial. The open string matrix is a little bit more subtle issue, okay? And it's more subtle, okay? And it has to do with the fact that gravity is not Wilsonian. So in other words, here's the point, okay? Okay, this is independent of string theory. So what is important is that notice that at the same time, in the same limit, there is absolutely no problem for defining an S-matrix, to keeping finite S-matrix, for other interactions. For the interactions that have so-called Wilsonian ultraviolet completion. Now, Wilsonian ultraviolet completion basically means that you can UV complete theory by going to shorter and shorter distances, by integrating in new weakly interacting degrees of freedom, okay, all the way. For example, QCD, okay? For example, we can do the following thought experiment. Imagine that you have a de Sitter space with a curvature radius, with Hubble radius, which is smaller than the confinement length of QCD, just for simplicity, okay? In order not to bother with alternization. So there you can define S-matrix. I can take the rigid limit. De Sitter becomes a good vacuum, but the gluon coupling doesn't trivialize, okay? So the issue is really a quantum gravitation. So it's really connected with quantum gravity because quantum gravity is what is controlled by exactly the same parameter that controls the rigidity of the de Sitter vacuum. So that's why gravity is special. So this is the point. Also, you can see clear signals. If we don't take this limit and we keep de Sitter as a state, but not as a rigid vacuum, you can see explicitly that we cannot define theory in the short time scale limit, okay? Because as soon as you will try to probe distances which are inverse of this energy meaning m Planck squared times the de Sitter radius, we run into an obvious problem because you produce black holes. Because gravity is non-Wilsonian and black holes prevent from probing arbitrarily short distances, okay? And so sooner or later, the radius of a black hole that will produce will exceed the de Sitter radius. Of course, that doesn't make any sense. You cannot even set up such an experiment. Okay, yeah. So now, what are we dealing with? And again, this is very important conceptually because I had discussions with many people. And And people that come from classical gravity background, okay? And here there is a difference, cultural difference between whether we come from classical gravity background like GR and then, or whether we come from particle physics. Because for a person, if we come from GR, right? If I'm a GR person, For me, everything I'm saying sounds very surprising, because you say, okay, but I mean, for example, why should I worry whether a background is S matrix or non-S matrix? For example, De Sitter or Minkowski. Minkowski is an S matrix vacuum. But what's special about Minkowski? Okay, Minkowski is one out of infinitely many possibilities in GR. And in classical GR, all these field configurations can be used as Vacua. But that's precisely the point. The point is that we are not satisfied with GR. We want to lift GR in quantum gravity. Whole point is about embedding GR into quantum gravity. And quantum gravity is more fundamental. So quantum gravity string theory is more fundamental than GR. Correspondingly, what quantum gravity tells us that not every background, classical background of GR, can be promoted into a good vacuum in quantum gravity. And that's great, because more restrictive is theory is more predictive, okay? And that's the way quantum gravity nullifies the cosmological constant puzzle, because it tells us, no, De Sitter, okay, you can have it as a classical background, but it cannot be an S matrix vacuum. Therefore, when you enter into quantum gravity, some non-trivial things may happen, okay? Now, the question I want to now briefly address is, normally, when theory tells us that we should not do something, and we do that anyway, theory punishes us, okay? So, for example, how would theory punish us if we close eyes on what I said, okay? So, just continue, like simply, let's assume that in quantum gravity, let's forget about string theory, you say, okay, very nice, let's just take simply some quantum gravity, and let me assume that there's a vacuum in this quantum gravity. How will the theory punish me? Now, so the point is that it will exhibit what we call anomalous quantum break time. This is closely related with anomaly, okay? Now, what is happening here? The point is very simple. Since in quantum gravity, De Sitter cannot be a vacuum, okay, that we know. So now, then the only possibility is that De Sitter, when I lift GR into quantum gravity, De Sitter is something which is an excited state constructed on top of valid S matrix vacuum. So here I'm taking it as Minkowski. You can ask me questions later about the anti-De Sitter, but here I will stick with unique S matrix vacuum as Minkowski. Okay. So now I'm not saying this is possible. This we don't know. Okay. So in other words, if De Sitter has any place in quantum gravity, then such a state must exist. So it must be a coherent state, presumably, because it must be maximally classical, but quantum coherent state constructed on top of Minkowski, which has the property when we take appropriate expectation values, okay, should give something like classical De Sitter metric, at least temporarily. Now, it's very important that I'm not claiming that such state, I fully know that such state exists. If it does not exist, then we can close this chapter about De Sitter, period, okay? However, it turns out that something like this, some constructions, we did some constructions, and they indicate that, yes, there are states which temporarily, when we take, they are coherent states, when we take expectation values over them temporarily, they look like De Sitter. They look like classical De Sitter, okay? However, there is again, a fundamental property, which is very important. What is this fundamental property? The property is that, so basically once you promote De Sitter or any other state into a coherent state, okay, you are doing, by promoting into a coherent state, you are effectively doing a corpuscular resolution, what we call a corpuscular resolution. For example, if I give you a gravitational wave, in classical theory, it's a gravitational wave. In quantum theory, that's a coherent state of gravitons, okay? So you are corpuscularly resolving a coherent state. You are resolving constituency. So what we are saying similar thing. If De Sitter has any place in quantum gravity, it has to be made out of stuff, okay? Now, it turns out that their properties are independent of resolution. So no matter how you resolve De Sitter, this satisfies the following property, which we call saturation. And actually I call objects that satisfy this type of relation saturons. So what's the relation? The relation is that the number of constituents, the mean occupation number of constituents, is given by inverse of their coupling and by their entropy. And you can check, you can just do this exercise, do whatever simple coherent state resolution of de Sitter and check this, and this will be satisfied, okay, this property. Now, this is very important because, but by the way, black hole also satisfies similar saturation relation, but for black hole, there is no problem because black hole is not a vacuum. So what happens then is very interesting, that the same corpuscular effects that are necessary to resolve de Sitter as a coherent state kill de Sitter after a certain time. What does it mean, kill? I will explain. They led to so-called anomalous quantum break time, okay? So in pure gravity, if you assume that there are no other degrees of freedom, which is a little bit unimaginable, but of course, if you take theory with pure gravity, then the quantum break time is latest is this time scale, okay? So it goes like r cubed and Planck square divided by number of particle species in the theory. Now, of course, if you are in pure gravity, then the only species is graviton. Now, what is quantum break time? Quantum break time is a departure of quantum between quantum and mean field classical evolutions. Okay, so it's a complete departure, complete breakdown of mean field approximation, like Gross-Pitaevsky approximation, for example, in many-body physics. That's what it would be. Now, of course, for most of the systems, actually, you can prepare systems in laboratory that quantum break. There is no problem with those systems. Problem is with de Sitter. Why? Because there is a conflict between classicality of the source and quantum breaking of the state. So in other words, you start with de Sitter as some sort of a coherent state, okay, constructed on top of Minkowski. And classically, it is sourced by a cosmological constant. Now, cosmological constant is a constant, okay? Then, after quantum break time, de Sitter quantum breaks, but source does not. And there is an inconsistency in this. And this is very important. So it's like anomaly. It's very similar to anomaly. It's very similar to anomalous breaking of gauge symmetry. Actually, there is also an interesting fact. I cannot enter in much details, but it turns out, and this was done in this paper with these people, where this concept of quantum break time was introduced. So it turns out that if system has instability, Lyapunov type instability, okay, then quantum break time can be logarithmic. For example, once we go away from pure gravity and introduce some scalar degree of freedom, for example, in inflaton, we have to be extremely careful because now we create built-in classical evolution and classical instability, and the quantum break time can become logarithmically short. It usually does. Okay, so that's what happens with quantum breaking time. Okay, in this case, in those cases. Now, the point is therefore the following: that de Sitter must exit, okay, gracefully. There must be a degree of freedom that gives graceful exit for de Sitter before it quantum breaks. That's a universal criteria. So here I measured this quantum break. So quantum breaking has several measures. I don't have time to enter in those details. If there will be questions, I'll be happy to answer. This is inner entanglement. So inner entanglement of the constituents among the constituents of the coherent state. Okay, you can sort of think of this as some sort of analog of the Page's curve, but it's not really. You should not be confused. It really has nothing to do with Page's curve, because Page didn't discuss internal entanglement. So this is Page's like curve applied to internal entanglement of the Sitter. So anyway, it has to find a graceful exit before it quantum breaks. Okay, so there is a universal bound, therefore. So if you give me, for example, your favorite model of inflation, all right? Then you can evaluate quantum breaking. Of course, quantum breaking time is model dependent because it depends on the coupling and number of degrees of freedom in your theory and the slope and the Lyapunov. But whatever it is, at each moment of time, quantum break time should be longer than the classical time of slow roll. And so this gives non-trivial constraints on the slower parameters of inflation. In general, that's very interesting for inflation and model building. Now, again, I want to reiterate the following thing, okay? If there'll be questions, I'll answer, because in the literature, certain infrared, it was discussed that certain infrared effects can lead to breakdown of the, instability of the sitter. For example, Polyakov, Woodard and Samis, Motola, and I hope I'm not missing, also Giddings and Slot, these people. They were considering these infrared effects. Now, this is not what I'm saying. The problem is precisely that I don't see any evidence for instability of the sitter. Instability would be a cure. If we could claim that if I put constant lambda and the sitter would simply decay or screen this constant lambda, this would be way out. Of course, this would fully agree with the conclusion that there is not the sitter in quantum gravity, but this would simply, in my language, this would mean that every time you put lambda, quantum gravity supplements it with degree of freedom, for example, an inflaton, which neutralizes this vacuum energy to zero. I mean, there's no contradiction with that, what I'm saying, but that's not what I'm saying. I'm saying that the quantum break time is not an instability time, it's an inconsistency time. Also, notice the following thing, that quantum break time is, which is either logarithmic or power law in n, parameter n, okay, is much shorter than the standard time scale of semi-classical tunneling. For example, the one considered by Coleman and DeLucia for the scalar potential, okay? So for example, if we have a scalar field, there is a tunneling, and this tunneling time is exponentially long. However, what this analysis tells us that there is a time scale which is much shorter and therefore is much more important. And this time scale has to be taken into account even when we discuss this type of potentials and tunneling through them. So in other words, that's part of the story, that this type of potentials cannot exist in quantum gravity, okay? Because before any tunneling becomes relevant, quantum breaking kills this potential. Now, here the situation is very similar. I want to make an analogy, which is, I think is a beautiful analogy, with the situation in 80s, okay? What situation was in 80s was with instant-on effects in QCD with large number of colors. Now, the instant-on effects in QCD with large number of colors, as you in QCD, they are exponentially suppressed, okay? So the naive expectation is that they go like exponent minus n. Okay. However, Witten and Veneziano, they came and they showed that actually there are effects which are exponentially more important, which are 1/n effects. Okay. For example, in generation of the eta prime mass, in breaking of chiral symmetry. So this is exactly what I'm trying to say, but in cosmology. What I'm saying is that so far, exactly in the same way as people were ignoring 1/n effects for chiral symmetry breaking before Witten and Veneziano came out with this statement, and we are concentrated on exponentially suppressed effects. That's exactly the same. We are in exactly the same position when we are considering tunneling from local minima through exponentially suppressed effects. Okay, so 1/n effects must be taken into account in cosmology. Okay, exactly the same way as they are taken into account in any large N theory like QCD. Okay, and so as you know, in QCD we have this anomaly interpretation of this story, and so therefore it's really same physics. Okay. Okay, so we don't have local de Sitter, we don't have global de Sitter. So therefore, what we are drawn to the conclusion that our vacuum is Minkowski. Okay, so there is one S-matrix vacuum, and everything else, including our cosmological history, is an excited state on top of this vacuum. Okay, this is great. Okay, and this is the way. So S-matrix formulation of quantum gravity tells us that, look, I mean, quantum gravity doesn't have to be background independent, and that's okay. Okay, don't worry, and don't let us not impose this condition on ourselves that we must have quantum gravity formulated on arbitrary background. There's no need for that. And actually, that's great. That's precisely the point. The quantum gravity tells us that in most of the backgrounds, it cannot be formulated. And there are backgrounds on which it can be formulated. And this, of course, from here, it follows that lambda equals 0 was never a problem. It's just a property of quantum gravity. Now, let me ask this. Remember, I had a question mark. Okay, now I'm coming back to question mark. Let me ask the question about dark energy. Okay, what is the implication for dark energy from what I'm discussing here? Okay. Now, there is, if dark energy exists in our universe, and this if goes to Colin, Mahoy, Ramiz, and Sarkar, who actually are challenging this statement at the level of observational analysis. Okay, this is of course extremely important to clarify this question. Now, if dark energy is not really there, that would be the simplest. Of course, that would be perfect match with not having cosmological constant and not having anything else. Of course, I'm not an observer, so I cannot really claim whether dark energy is there or not. But all I can say is that if dark energy is there, it will come. It has to come from new physics, beyond the standard model. And of course, because we cannot simply take standard model at Einstein gravity and at lambda. That will not work in quantum gravity. And dark energy should evolve in time very fast, okay? Pretty fast, over the time scales, which are most of the cases, if we introduce a degree of freedom, in which, because we have to introduce degree of freedom, because dark energy, if it is there, it has to evolve, the time scale is very short, okay? So the difference from cosmological constant, it will be substantial. Okay, so I don't know, if I have 5 minutes, I can discuss. I think we had initially at some kind of 5 minutes somewhere floating around. So let me just mention the hierarchy problem and finish with this. So now I want to briefly mention implications for other naturalness problems from this landscape. Because, so for example, for the hierarchy problem. Now, what is the hierarchy problem? Hierarchy problem is the hierarchy puzzle, which is called problem. It's not really a problem, it's a puzzle. It's again about UV sensitivity of the Higgs mass towards the ultraviolet cutoff of the theory, okay? So we expect that by naturalness, the Higgs mass has to be of order the cutoff. And so this makes the hierarchy problem real because of gravity. Why? Because in gravity, with finite Planck mass, there is no way to have an elementary particle heavier than the Planck mass, because such a particle would have a Compton wavelength, which is within its Schwarzschild radius, and such a particle would be a classical black hole. I mean, classical and good approximation. So Planck scale really is a non-perturbative, and this statement has nothing to do with perturbation theory or perturbation series. This is a full non-perturbative statement. The Planck scale is an absolute bound on the mass of any elementary particle. So that's why we are not worried why Higgs is not as heavy as the solar mass. It cannot be, because if it were a solar mass, it would be a solar mass black hole. So this creates a real question. So why then Higgs is much lighter than the Planck mass, if Planck mass is the cutoff? And so one approach to this is that there must be some new physics nearby to stabilize. So the cutoff, effective cutoff that stabilizes the Higgs mass has to be low, okay? Now, this picture was also replaced by anthropic. So in certain picture, I'm not saying in every, but there was a point of view that says that this picture can be replaced by cosmological selection. So what type of using the de Sitter landscape? So there are two types of cosmological selection. One is anthropic selection. Again, actually, Argewald, Barr, Donoghue, and Seckel, they came up with this brilliant idea that the Higgs mass again is a parameter towards which observers like us are sensitive. Higgs mass creates an environment, and it is important somehow to be in the right range. Okay. And that's brilliant. And if we now supplement this with the idea, with the de Sitter landscape, we'll get certain selection. Eternal inflation, de Sitter, this can give anthropic explanation of the Higgs mass, according to this picture. There is an alternative picture. Actually, this was developed by Alex Vilenkin and myself a pretty long time ago. about non-anthropic but cosmological relaxation of the Higgs mass. The idea is different. So the idea is that there is a cosmological selection of the Higgs mass. There is a cosmological process that is scanning different values of the Higgs mass, and there is a backpropagation mechanism through which the Higgs mass acts like a control parameter for this selection. And the trigger was actually a QCD scale, and which tells the cosmological evolution where to converge. Okay. So, for example, number of vacua around this certain value of the Higgs mass, around 100 GeV, diverges. It's infinite. So it's like the certain vacua duplicate the infinite times the same value of the Higgs mass, and correspondingly they dominate the cosmological selection. Now, both are in trouble because of what I said. Because I said that both require, at least the only well-established scanning mechanism is eternal inflation on the de Sitter landscape. This is what we also used together with Alex. Correspondingly, now if quantum gravity abolishes eternal inflation on the de Sitter landscape, this both anthropic selection and cosmological relaxation, they require some replacement of that mechanism. Okay, so some other selection mechanism has to come in. Otherwise, we cannot talk about them. Okay. Of course, this strengthens the point about existence of new physics, new stabilizing physics. Of course, doesn't prove anything. It just strengthens the point. But it also is a very good illustration why these points are extremely important. Okay. Finally, there is a similar take on theta vacua in so-called strong CP problem, because the absence of de Sitter landscape, if you translate it to theta vacua, would tell you then also theta vacua should be absent, should be unphysical. Why? Because as Waffa and Witten showed us, that the vacuum energy depends on theta parameter, and it actually is minimized for theta equals 0, which means that if there are theta vacua, necessarily there will be some theta vacua which are in de Sitter. Okay. Now, if quantum gravity cannot tolerate de Sitter, somehow quantum gravity has to remove those theta vacua. Well, we know there are ways of removing theta vacua. For example, axion or chiral symmetry, okay, massless quark, anomalous chiral symmetry, and so on. So, and this is again interesting because this would mean that the quantum gravity forces that every time we have theta vacua to have also certain degree of freedom like axion or massless quark that make sure that the theta vacua become unphysical. Okay. So let me conclude finally that, okay, so these are the main messages that I wanted to bring across, that S matrix formulation of quantum gravity excludes the de Sitter landscape. This nullifies, of course, the cosmological constant puzzle, and at the same time predicts new phenomena because of this quantum breaking effect. And it changes the view on background dependence of quantum gravity, and also gives a new angle on the naturalness questions. So those questions that previously were thought to be, for example, addressed by de Sitter selection on eternal inflationary selection, and on other problems, like, for example, so-called strong CP. Thank you very much, and I hope I didn't go too much over time.
Thank you, Gia, for the beautiful and inspiring talk. So we already have a few questions in the chat. And
okay, let me see.
Let me try to, so if I'm able to allow people to talk. And then, of course, we will. So I think we can start with the people in the chat, and then move to the people who are raising their hands. Okay. So.
Yes, sure. The only problem is I don't see chat. Maybe if someone.
So there is one. The first question is by Goran Sejanovic, who's called actually admin. So let me see whether. Okay, Goran. So can you talk? Can you see if you can talk now? No.
I don't hear anything.
Can you hear me?
Yeah, now yes.
Okay, perfect.
Okay, so good. Okay, I just want to make sure, because I love to hear this. I've, as you know, Gia, I've been arguing for quite some time, especially in recent years, that the naturalness issue, in a sense, is confusing us and misleading us. So what you are saying, what would emerge for what you are saying is that actually the problem is not because lambda is small or theta bar is small, but quite the opposite.
Yeah, exactly. So in other words, what quantum gravity is telling us is that if you would have larger values of lambda, actually that would be a puzzle. So in other words,
Right.
if we would see lambda for sure, somehow we could prove that we really have lambda in our universe, that would be an extraordinary puzzle, because then we would need to understand what is happening with formulation of quantum gravity, how to formulate quantum gravity. Exactly.
If you're right, the size of this was never an issue, whatever the theta is, because one often argued before, oh, I need a Pechak-Quinn symmetry or axion in order to explain why theta is small. That's actually the same question that was there originally, because you can ask why Pechak-Quinn, right? This is now
exactly. Indeed.
the crucial thing is
right.
It's
exactly.
not,
Indeed. I mean, Goran was arguing about had papers about the smallness of theta, etc. That the smallness per se is never an issue. But of course, it's very important. I'm not talking about that. I'm not talking about we can have different points of view whether smallness was an issue or not, was not an issue. What I'm saying is that regardless whether you view smallness of theta, of measured value of theta, for example, electric dipole moment of neutron, regardless what you think about it, the existence of theta vacua is an issue, because it's very hard to imagine, given what we know from Vacua, that the energy of theta vacua depends on theta parameters. Energy of the vacuum depends on theta parameters. This would mean that would be unimaginable that none of these theta vacua are in the sitter. Okay, so for example, today we live in the vacuum in which we are pretty close to Minkowski, and also theta parameter is 10 to the minus 10. It's very small, right? So today we live here, somewhere here. Okay. Now, I'm not even assuming that we necessarily live in Minkowski. There could be some field which evolves in time, etc. But what I'm saying is that if finally we go into the right Minkowski vacuum, S-matrix vacuum, if theta vacua are physical, necessarily there will be some theta vacua which are in the sitter. And then this creates a puzzle, because how can a quantum theory of gravity create vacua on which quantum theory of gravity is ill-defined? So correspondingly, the natural thought would be that quantum gravity should eliminate theta vacua by supplementing every time we have theta vacua, supplementing them with an axion, corresponding axion, or a master quark. This is my point. So my point is that regardless what you think about naturalness, if theta vacua are in the sitter, they are problematic. But yeah, thanks very much. Yeah,
I would just like to broaden the discussion a lot, because naturalness has played a major role for decades in somehow pushing a direction of the physics, as you know, beyond the standard model. And I think it's important to understand that from what you are saying, this is crucial. The value of theta is not really an issue. Now, the reason I like to hear that, if I take the standard model, you agree, per se, the value of theta tells me nothing about the standard model. It constrains nothing. It cannot be even an issue in the standard model.
Yeah, without gravity, no issue. Yeah.
Right, without gravity, not. And I've been showing, for example, in the recent paper with Theo, that if you take a well-defined theory like a left-right symmetric model, it's even good that it's small, because it allows you to get constraints which otherwise you would miss.
Sure. But again, it's important that that's a different discussion. That's a different discussion. What I'm saying is that what is important from the point of view of quantum gravity, not the value of theta per se that we are accidentally measuring, but the fact that there is a continuum of vacuum states, and if this continuum is physical, then some of those will be expected naturally to be in the sitter, to be the sitter vacua. because there is a difference of energy between this point and this point. This point is pretty close to Minkowski, then this point around here will be de Sitter. And so that's the problem. So that's the problem what I'm saying. This is regardless what we think about naturalness. It's no longer a naturalness issue. This is what I'm trying to say. Quantum gravity promotes theta vacua into an issue of consistency through de Sitter. Okay.
Right. Okay, we are agreeing. You just
no.
Well,
I mean, there was no disagreement because, as I said, I mean, I'm addressing an issue that has nothing to do with naturalness here. I'm just saying that regardless what you think about value of theta, whether it's good or bad to have it small or large, the value per se is not an issue. What is issue is that there are multiple thetas given by the same theory, and some of those would be in de Sitter. This is what I'm trying to say. Okay.
Well, okay.
I mean, we can come back to this discussion. I'll be happy to discuss as long as
there may be other people that want to have comment. I just want to make one more comment. There was this issue that Weinberg himself was advocating for years that I should worry. He was telling me why lambda is small because I'm a field theorist. And that was created as a naturalness problem of cosmological constant to argue that the formation of galaxies is an answer. It's completely wrong. It's not scientific explanation. I would want to argue against that at all cost. It's just an accident. How can you explain a fundamental quantity that I should be worried about just because it was good for us that it happened? It's like me understanding that it rains because of clouds. And now I see today that it's raining without clouds. And you tell me, no, but it's good because rain is good for you. That's not a scientific explanation of the question that you are asking.
Yeah, I mean, Goran, so yeah, I mean, these are, of course, extremely important points. And there is, of course, there is an ongoing debate about anthropic, and it's important that you are bringing this up. I'm absolutely with you in this. But my point was that quantum gravity is above all of this. My point is that this discussion becomes irrelevant because this is the picture quantum gravity gives. And in this picture, there is no possibility to actualize different values of lambda. Simply, there is no mechanism for actualization of different values of lambda. Therefore, in this picture, discussion about anthropic selection it's nullified, becomes irrelevant. This is what I'm trying to say. So I'm not trying to argue against anthropic selection.
Well, I wish you would. No, I wish you would because you're making it a scientific. What you have done, which I like it a lot, is that this now becomes a scientific issue. You are using a consistency of the theory as a question what the value of lambda is.
No, I never expressed my opinion about sympathy or anti-sympathy with respect to anthropic. Actually, I was never in anthropic, fan of anthropic. I was never in anthropic camp, but I deliberately didn't express any opinion about that because that's completely irrelevant in the light of the message that I want to bring. I'm saying, doesn't matter whether you think that anthropic selection is scientific or anti-scientific. It doesn't matter. The quantum gravity tells us that there is no engine for anthropic selection of cosmological.
Okay, fair enough.
So therefore, I don't see why I should enter in that debate. Okay, but
well, I wish you would, but you don't have to. I agree. Okay. Okay, I'll let the others. I can see Misha had a question. So I mean.
Hi, Gia.
Hi, Misha. How are you?
I'm good, thank you. I have a small question, but at first I would like to reformulate your whole story in 1 or 2 sentences, and then I will ask my quick question. Mm-hmm. I think that the summary of what you said is as follows. Okay. We have the standard model and some maybe unknown physics beyond the standard model, but at energies low compared to the Planck scale. And each individual contribution from these low energies to the cosmological constant lambda is very large compared to what we observe in nature, right? But you say we don't have to bother because quantum gravity takes over at the scales of order of the Planck mass. We don't exactly know what it is, but you argued that quantum gravity by itself nullifies the cosmological constant. It's kind of forbids the Sitter spaces, right? Or makes the whole description in terms of the Sitter classical background meaningless, right? Basically. Now the question is, if it were indeed the case, wouldn't it be more reasonable, because there is some principle, as you said, behind this, why it still permits a very small cosmological constant to exist in nature as it is measured in experiment? Why it is not exactly zero?
Okay. So thanks very much for this question. So I can start from the end. So Misha, can you hear me?
Yes, I hear you. Yes.
So let me start from the end. Actually, what I'm saying is that I am predicting the cosmological constant is exactly zero in our universe.
Okay.
So by no means what we are measuring, first of all, by no means it's obvious that what we are measuring is a cosmological constant. Even if dark energy is there, there is still the error from, we don't know whether the equation of state is really the one of the cosmological constant. So by no means we know that dark energy, if it is there, is a cosmological constant. And as I said, recently there were also challenges by Subir Sarkar and collaborators. Even that is challenged, how much of dark energy is in the universe.
Okay.
I'm not entering in that territory because I'm not an observer. What I can predict for sure, I can predict a bound. So I'm giving a very concrete bound, how fast, if dark energy is there, how fast it has to change because of the constraint from quantum break time, which is like anomaly. So this is to answer your last question. But let me come back to the previous point. Actually, thank you that you brought this up, because again, even here, you see, when we say that we know that individual contributions are large, actually that's not a correct statement. The reason is very simple, because what do you mean under individual contribution? For example, if I naively use perturbation theory to compute lambda, sure, I can do loop expansion. Now, however, the problem with quantum gravity is that there is no small parameter in quantum gravity of loop expansion. So sooner or later, for example, even if I compute one loop or two loops, sooner or later I should ask this question: what happens with the particles once their virtual energies go above the Planck scale? So now we know that in general, what happens with an elementary particle of mass larger than the Planck scale is that it becomes a black hole, classical black hole. There is no way to have a particle or any other entity localized within its Schwarzschild radius that is not a black hole. Okay, anything within its Schwarzschild radius is a black hole. Correspondingly, nobody knows how to take into account contributions to the loops from micro black holes. Okay, so there will be extremely important threshold corrections from quantum gravity through these loops. And therefore, it's by no means obvious that what you call individual contributions are large. Nobody has seen it. We just assume they're large.
I fully agree with this, that we don't know, strictly speaking, nobody has the right to extrapolate one loop or two loop.
Exactly. So
this is nonsensical.
Right.
But people do that all the time.
But they should not. That's what I'm trying to say. We should not, because we do. Absolutely, I fully agree. All the time we do things because we use sort of intuition of effective field theory, etc. Sometimes we use perturbative intuition in the. I mean, you are a world expert. You know much better than me what happens in QCD. Already in QCD, once we hit strong coupling, so all the intuition about the perturbation theory goes down, and correspondingly, is very similar here. So that's my first point. But also, what I'm saying is that very good guideline of what I'm trying to say is anomaly. Because you see, imagine the following situation. Imagine someone would come to you and tell you, okay, look, here's standard model. And let me introduce a particle, a chiral fermion with a hypercharge, which is minuscule, okay? Like, I don't know, 10 to the minus 100. Okay, naively would say, yeah, I mean, if hypercharge is so small, why would this fermion affect anything in physics of the standard model? But we know that it does, because there is a discontinuity, because there is an anomaly, gauge anomaly in the theory. The moment I introduce chiral fermion, no matter how small is the charge, if theory is anomalous, if there's gauge anomaly, all of a sudden the whole structure of the theory changes. All of a sudden the theory becomes UV sensitive, etc., etc. It's very similar. So basically what I'm trying to say is that if we look from this point of view, there is simply a consistency requirement that lambda has to be 0. We should not be in the sitter. That's a consistency requirement that at the end of the day, the lambda has to, no matter with all contributions computed, it has to be 0 by consistency. Or we can look top down. I'm saying, let's assume that it doesn't happen. If it would not happen, we would end up in the sitter vacuum. But in the sitter vacuum, 1 over n corrections would be anomalous, and they would destroy the sitter symmetry and would lead to inconsistency. And so, yeah, so from both sides, we see that this is what's happening. Mm-hmm.
Okay, thank you. Thank you.
No,
I understand your point.
Very important.
Okay, so next question on the chat was by Lucas Eisenman. So let me unmute him. Okay, please, Lucas.
Thank you. Hi, Gia.
Hi.
I would have 2 questions. So the first question concerns your statement that the cosmological constant problem is nullified. So.
No, but the puzzle I said is nullified about positive cosmological constant, right?
Right. Yeah.
Mm-hmm.
Sorry, did I say something else?
Mm-hmm.
So would you agree that? So you just pointed out that actually this estimate of lambda being of order the cutoff in power 4 is maybe questionable itself. But if that was not the case, would you agree that in principle your finding that any lambda, any non-zero lambda is inconsistent, this finding actually still leaves the cosmological constant problem, just as it leaves the problem to explain why, for example, we do not have any theta vacua that are with we do not have theta non-zero. So in the sense that you argued that any theta non-zero would lead to positive vacuum energy and thus to the sitter-like state.
So, but these are 2 separate questions, right? Or it's one question.
This is supposed to be the same question. So
the same question.
In the sense that
Okay, let me answer it. Yeah. Okay.
Yeah.
Mm-hmm.
Please.
Yeah. So in other words, so I so you see how the intuition works sometimes, that it gives us lets us to some wrong conclusions, because you said that all I'm saying is that we don't know, nobody has computed these contributions, even at 1 loop. There is no computation in the literature or anywhere how the micro black holes affect this 1 loop computation of, and how black holes in general affect this 1 loop result, for instance, or 2 loop result.
Mm-hmm.
So we simply don't know. And now it's reasonable, therefore, for me to assume that we don't know. So therefore, I'm saying that this expectation was never based on anything. Of course, we intuitively assume that, oh, because the loop is divergent,
mm-hmm.
Presumably it's large, but that's all there is. And I mean, there is no question. I don't even have to. So this is like now starting debate whether this is large or small.
Mm-hmm.
For me would mean to enter into an unknown. And by the way, the assumption that is made, so here is not me who is making an assumption, it's you, because you are somehow assuming that this is large, and then somehow you are putting the proof of the burden of the proof on me to prove that this is small. But I'm saying we simply don't know this, therefore don't think about it even until you know how to compute it.
Okay, let me try to
Yeah.
rephrase it a little
Now,
bit. So,
no, let me finish the answer. So therefore, what I'm saying is that we don't know how to compute this, and then leave it. Let's leave it as it is, okay, as an unknown, and let's look for fundamental principles, if there are such principles, which would tell us something about this lambda, okay.
Yeah.
And I'm saying that there is a fundamental principle, which is mathematics.
Yeah, sure.
It's a formulation of theory, and therefore mathematics very clearly tells me that all these computations, whatever they are, they have to converge to zero, because of zero or anti-de Sitter, negative. Okay.
Yeah.
Now, this includes everything else. So theta vacua. Now, theta vacua are additional problem. They come on top of this, because in theta vacua we know that how energy depends on theta parameter. Okay. And we know that there is a minimum for this energy around theta equals 0. And if there are other theta vacua in the theory, some of those theta vacua would be expected to be de Sitter-like. Okay? Just by observations, because I'm saying we live in the vacuum of small theta, and we live pretty close to Minkowski. Now, therefore, if there are vacua for large theta, from what we know about vacuum dependence of energy dependence of theta, those will be in de Sitter. Therefore, to avoid that, there must be a degree of freedom which abolishes this energy dependence of theta vacua. That's all I'm saying. I'm saying that quantum gravity has to take care of this by consistency. And therefore, I'm saying quantum gravity probably provides axion or a massless quark for each gauge theory that has theta vacuum. Okay.
And so concerning these quantum corrections to lambda, your statement would be, if ever anybody should be able to calculate it, he will find that it sums up to exactly 0. We don't have
or something negative, or anti-de Sitter.
Yeah. Okay.
Yes, I mean that's a conclusion drawn from what I tried to explain throughout my talk. In other words, throughout my talk, I tried to explain that I have a prediction, and the prediction is that this has to sum up to 0. So in our universe, on our cosmological branch, to 0. Yes.
So then your view would be that this so-called cosmological constant puzzle is still there, but so somebody would have to prove that it sums to 0. But you also pointed out why.
I don't. Why is there? If quantum gravity tells us that lambda is 0 in our universe, it's 0. There is no puzzle. It's just simply statement. Quantum gravity gives us a statement that lambda is 0. It's just like quantum gravity gives us a specific statement about a specific parameter. It is 0. Where do you see the puzzle? I don't understand what is the puzzle.
I mean, from your argument, you also conclude that theta is exactly 0, right? And then you say that
I'm saying that theta vacua must be unphysical. That's what I'm concluding from there. I'm saying theta vacua must be unphysical, because if I have distinct theta vacua, okay, distinct legitimate theta vacua, then some of those will end up in de Sitter. Somehow quantum gravity should have a way to eliminate multiplicity of theta vacua. There must be one physical story, one physical vacuum. How quantum gravity does that, I don't know. I can only judge from what we know. We know that axion works, okay? And we know that if there is a massless fermion, massless quark, chiral quark, that also works. For example, there are at least 2 ways of doing that. So that's what I'm saying. So yeah, so these are two different, two different things.
All right. Okay. I would like to ask a second question, which is rather
Lucas, super quickly, because
yes,
there's a long list of people.
Yeah, very important question. So I don't understand necessarily why you get from. So I follow you when you as long as you say any. So as soon as we go as soon as we quantize gravity, any de Sitter-like state cannot be an eternal de Sitter-like state anymore, and in particular cannot be a vacuum. As long as we keep G Newton finite. But what I don't understand is the step to say that any non-zero lambda would lead to inconsistencies. So your argument is that the lambda would be a classical source for this quantum degree of freedom.
Yeah. Okay. So
yeah.
let me see if I understood the question. So you mixed two different arguments. There was one argument based entirely on S metrics. In that argument, I don't even have to mention about quantum break time. Okay. So I'm saying that there is an S matrix argument which tells me that any eternally inflating space-time makes it impossible to define S matrix. Okay, that's one statement. All right. Okay. So that has nothing to do with the quantum breaking time, etc. Quantum breaking time is a microscopic way to understand how theory responds and tries to improve the situation. Okay. Right? Because every time we do something wrong with the theory, for example, when we create anomaly, theory responds. For example, if you introduce, as I said, chiral fermion in the standard model with small hypercharge, theory will respond, okay, by, for example, generating mass for the photon and this kind of. So I'm saying there is a microscopic mechanism which, in which way theory responds. Maybe there are more than one mechanism. I'm not claiming that I have understood all the mechanisms by which theory responds to the wrong vacuum, but at least we understood one mechanism. That's anomaly. That's anomaly with respect to 1/n corrections. So that's one mechanism. So yeah, that's what I'm saying. So these are two separate things. They should not be confused because S matrix argument is there regardless whether you believe in quantum breaking or not. You can tell me, oh, no, I don't want to discuss this 1/n corrections or whatever. I don't see why, but that's a separate story. Okay, these are two separate stories. Okay, does this answer your question?
Maybe I didn't get the point.
Anyway, we can continue because other people want to ask.
So maybe there is also, I had to say that there will be a Q&A session if people want to challenge Gia even more. Yeah. So, but this has to be offline. Okay, so I think we should move on. There is Zura Bereziani next. So let's see. Please,
Okay.
Zura.
Hi, Gia.
Hi, Zura.
Thank you for a very interesting talk. My question is very simple. First question, actually. Okay, you have shown why we do not live in the ether, or we have not to live in the ether. Why we do not live in anti-de ether?
Yeah, so thanks.
And the second question is that I do not really quite well understood the implications for the Higgs naturalness, because it's not only a problem of cutoff, because if you minimally accept the idea of grand unification, the problem is fully reformulated, right?
Well, you get additional problem, right? You get additional problem. But
about many other things, and it's not only quadratic divergence or whatever cutoff scale for the Higgs mass and so on. Okay, first question is more important.
Okay, so maybe let me
just a very simple comment.
Yeah, in other words, one thing is this.
One question. So you say that whatever dark energy phenomenologically we see today, it is an excited state simply, which sooner or later should decay, and you give the time after which we have to gradually exit from this situation. And it is only sort of upper limit because it can have other decay modes which can be shorter. Correct?
Yeah, it could be faster, of course. It
could be faster, but the time which you have given, it is maximal allowed time.
It is the maximal time, exactly.
And it also explains why cosmological constant is not bigger than something. You can put a limit on the dark energy, whatever it would be, from that consideration, knowing the lifetime of our universe in some sense, right?
No, it's okay. Let me see if I understood correctly, because I'm saying, so here was this, sorry, let me go to the predictions. So here, right? So I'm saying the following thing. So if there is dark energy, again, but I should say that again, there are people that are superior collaborators, which are challenging how much dark energy is there. But let me take as a working assumption there is dark energy, because I don't see any inconsistency from having time-dependent dark energy. Then there is the universal upper bound. So this universal upper bound tells us how eternal the dark energy can be. And this is regulated by a very simple principle that at each moment of time, there is a local evolution, classical clock. So there are two clocks, basically. Think in the following way. There is a classical clock that dark energy goes down the slope, okay? Or decays otherwise, I don't know, so it can be other. And there is a quantum clock. The quantum clock, which internally tries to create inconsistency. So what happens is that the classical clock must be always faster. In other words, system should escape before it has this time to create internal inconsistency. So that's the principle. Now, the classical time, of course, depends on the slope of the potential. Quantum time also depends on the slope of the potential and the coupling. And so, typically, if you give me, for example, if you give me your favorite dark energy model, we can test and we can check and we can give concrete predictions what the parameters should be. Okay. So this is the idea. So in other words, so yeah, and so this is the constraint. I cannot add anything more to it. So what we see from here now, if we compare with observations, what do we see from observation? I can give you a minimal time scale on which the dark energy should change. Okay, it can be shorter. Okay, so it's an upper bound. In other words, it's an upper bound on how constant the dark energy could be.
Maximum.
Now this bound translates as a bound on equation of state. Okay, so the same logarithm that I plotted there also enters in the equation of state and also tells you how different dark energy equation state of dark energy should be from the equation of state of cosmological constant. Okay, now for my argument, there would be absolutely no problem if dark energy is exactly zero. Okay, so that would lead to absolutely no visible inconsistency. So therefore I cannot say that dark energy must be larger than something. That's not possible. Dark energy in each model is only constrained by this relation, this equation. This is the master equation. Master equation is that T slow must be less than T quantum breaking. This is independent whether we're considering dark energy today or we are considering inflationary evolution. During inflation should be the same constraint. Okay, so according to what I'm saying. Now regarding the Higgs story. So what you are, my point was the following, very simple. My point is that there is an absolute upper bound on a mass of any elementary particle, okay? And this absolute upper bound comes from the fact that we know that in deep infrared, gravity is Einsteinian. Because gravity is Einsteinian in deep infrared, we don't have to know what is happening here to conclude that the moment you give me an elementary particle which is heavier than the Planck mass, from infrared gravity that will look like a black hole. Why? Because its Compton wavelength will be inside of its Schwarzschild radius. Okay, that's the definition of a black hole. Now, and this is an unremovable part of the hierarchy problem of hierarchy puzzle. In other words, I'm saying that this makes hierarchy puzzle real. Now, of course, if we have new physics here, for example, grand unification, the story may become even more complicated and even more problematic. I fully agree with you. Of course, as you know very well, in grand unification, we have this famous doublet triplet splitting problem, and et cetera, et cetera. I mean, of course, those are on top of this, obviously. But this issue is there. This absolute bound is there. Okay, so it's always there.
The last question: why we do not live in anti-de Sitter?
Yeah, so the anti-de Sitter, sure, absolutely. There is absolutely no inconsistency problem with anti-de Sitter. Sorry. There is no inconsistency problem for having anti-de Sitter vacuum. As in fact, we have this ADS CFT correspondence, which tells us that actually ADS we can even map it on CFT. So there are no issues with anti-de Sitter of that sort. But from the cosmological, so the question is not that whether there can be an isolated. So there is absolutely no problem if there is an isolated anti-de Sitter vacuum. The constraint is that this isolated anti-de Sitter vacuum must be such that it should not jeopardize S-matrix properties of the Minkowski. Okay. So, for example, if there is a cosmological evolution which shoots you over, that will jeopardize S-matrix properties of this Minkowski. Okay. So therefore, with anti-de Sitter cosmologically, unfortunately, I didn't have time to discuss this. This is another fascinating story, how deep anti-de Sitter can be. Actually, it turns out that S-matrix also puts bound on that, how deep it can be. So I didn't have time to discuss that. But the minimal requirement of anti-de Sitter is that there can be isolated anti-de Sitter vacua on the string landscape or on quantum gravity landscape. and there is no problem with that. But they must be, how to say, they must be sterile, sort of. They must be sterile. They should not interfere with the asymmetric properties of our vacuum. So that's the general. That's the general criteria.
Okay. You say that we are sitting in our vacuum by some cosmological initial conditions because we could end up just directly in the anti-de Sitter vacuum.
So okay, that's a now fourth question. That's different. Okay. So in other words, that's a fourth. No, that is a very important question. In other words, if you are asking the following question, that can we have a cosmological history which somehow ends up in the anti-de Sitter and still define asymmetric theory on that cosmological history, I don't think that's possible. Okay, but that was not subject of my talk. But I'm saying in general, I think there are obvious difficulties for defining asymmetric theory on a cosmological history which ends up in anti-de Sitter.
No.
Okay. All right. Okay. Thank you.
Okay. Thank you.
Okay. I think yeah.
So there is Arkady Weinstein next. So.
Hi, Arkady.
Hi.
Hi, good to see you.
Look, you're probably tired, right?
No, I'm not tired. That's fine.
You are not tired, okay.
Oh, with you, I'm never tired, as you know.
No, you are never tired. I am sometimes.
Well, okay.
But look, I mean, you know, I have some kind of problem following the following that. Let's start from kind of GR itself. So I always can think about gravity as placed in a Minkowski space. I mean, there is no problem to say that we have some theoretical Minkowski space, right? And then we have matter, which includes gravity in this Minkowski space, and we can consider different, you know, stuff in this quantum gravity, including, but in this way, strictly speaking, I do have a Minkowski space. But in classical GR, you know, the idea where Einstein was that this Minkowski space becomes physically not observable, right? I mean that it does exist, but what is your real distance, what your real time is not does not give you a possibility to measure this you know, kind of original Minkowski space, because all these measuring devices are influenced by gravity, right?
Oh, you mean because of the well? Okay, that's not no. That's an important point, but I don't think that's completely true, because if you are considering classical theory, classical GR, in classical GR you can make arbitrarily precise measurements of all the curvature invariants. So in classical GR there is no ambiguity. In classical GR you can.
No, I'm not saying that there is ambiguity. I'm trying to say that there is no problem to view gravity as placed in a flat Minkowski space, and then to discuss what is physical measurement are, right?
Oh, sure, yeah, I agree,
okay, yeah. So in this way, what I'm trying to say is that the notion of Minkowski space doesn't disappear per se. There is a notion of Minkowski space, and you are using this reference to Minkowski vacuum in particular. That's why I'm actually coming to the question that in this way, to me, your construction sounds. No, I mean, I'm trying to compare with, I discussed with Sasha Polyakov long ago when he was obsessed with this idea of, you know, kind of, that the Sitter is not stable. Even difficult for me to consider.
Yeah, as I said, I fully sympathize to
yeah, right.
That idea, but that's not what I'm saying. I mean, I'm saying.
Right, but I'm trying to find the difference, because you see, if I believe that something like, because when you are referring to asymmetrics, it's again it refers to me in Minkowski space in certain way, because if you consider, say, if you would believe that it is like the Sitter and say distances are limited, right? Then the notion of asymmetrics within the Sitter is not well defined, because there is no degeneracy. You find the distances lifts that asymmetrics exist because there is degenerate states, right? But when you have a finite size box, you know, then even this degeneracy disappears, right? So asymmetrics in a usual sense does not exist. It becomes like a bound state in a sense, right? Because you can say that to me, in this way, still general construction you are talking about looks like you have, say, Minkowski space. Okay, in Minkowski space, you can have some object like, I don't know, configuration, right? And this configuration could remain the seated, but it would be unstable. I mean, it appears and disappears, right? So no, I mean, and maybe there is a difference in what you are saying, but still the general feature is similar, that you have kind of unstable configuration which appears and disappears, right?
No, I'm not saying that. So this is very important to understand the difference. By no means I'm saying that, no, but this is very important. No, thanks for bringing this question. By no means I'm saying that I know how to construct fully fledged de Sitter as a coherent state on top of Minkowski. I'm not saying that. I'm saying that if that is possible, if someone tomorrow comes and tells me, okay, here's my recipe, how you construct it, then this state will have a quantum break time. That's not an instability time. Again, I want to make it very clear. I'm not saying that de Sitter becomes...
No, it's exactly what I'm asking about, right? Because for me...
Right, it becomes inconsistent on that time scale. So therefore, by consistency, whoever constructs de Sitter as a coherent state on top of Minkowski has to make sure that the graceful exit from that Minkowski, classical graceful exit, I mean, normal slow roll graceful is shorter than quantum break time to avoid inconsistency. This is very different from claiming that any de Sitter is unstable. I'm not claiming that. I'm saying de Sitter is inconsistent. In order to maintain consistency, we have to terminate it. And to terminate it, we need a degree of freedom. So by consistency, quantum gravity has to provide degree of freedom, for example, inflaton or whatever, or axion or whatever. Now, so therefore, it's yeah, absolutely. In other words, you see, my logic goes in the following way. I'm saying that, yes, despite the fact that, yes, of course, in de Sitter, that's my starting point. I'm saying, of course, in de Sitter, we don't have globally defined time, because therefore, we cannot really define fully fledged S matrix. However, there is no problem to define an S matrix as a limit, even in de Sitter, for Wilsonian interactions. For example, for QCD, there is absolutely no problem. I can define QCD as an S matrix type theory in the limit of infinitely short time scales. Okay, in deep UV, deep infrared, the limit is consistent. So therefore, this argument that simply because de Sitter doesn't have global defined time, therefore all the theory should be thrown out within de Sitter, that's not true. I'm saying that quantum gravity is the special one. So quantum gravity is the only one which is controlled by the same rigidity parameter that controls the rigidity of de Sitter. And so this is extremely important, because I don't want this message to be lost. I'm saying that for QCD, there's no problem. We can take that limit of de Sitter and consistently define QCD on de Sitter. I don't see any problem with that. We can perform all possible S matrix computations in the limit. So this is very important. So this is what I'm trying to say.
I see.
Now, of course, you see, the point is precisely that, because I mean, in GR, for example, right, in gravity, right, in general relativity, right, in general relativity, for example, there is no fundamental difference between Minkowski space and gravitational wave. Okay, so because gravitational wave is a very nice classical background, so one can say that what's the difference? I can use as vacuum gravitational wave. But of course, once we go to quantum gravity, we understand that Minkowski is Minkowski and gravitational wave is a coherent state. And there is no ambiguity there. I mean, nobody would argue that gravitational wave is a coherent state of gravitons. So what I'm saying is that one step forward is necessary if we want to talk about de Sitter. If we don't want to talk about de Sitter, there is no problem. We can simply close this. We can simply say, no de Sitter in quantum gravity. Okay. But I don't think the situation is so dramatic. I think we can define temporary de Sitter states in quantum gravity, for example, inflationary state, and inflation can do its job in quantum gravity. So yeah, I think that's perfectly fine, but the number of e-foldings is really dramatically limited. Okay.
Okay, I got it. I got your point. I only minor comment about theta because you always refer to the energy of vacuum as a positive with non-zero theta angle, but I believe that in GGD it is the opposite. It is negative for the non-zero theta, right? I'm not sure whether it's important for you. Just a reaction on to this. So, but
no, I'm talking. No, sure. I'm talking about relative energy. I'm talking about relative energy. I'm just talking about Waffa-Witten theory. So Waffa-Witten, that show that.
Relative, you mean due to gravity, right? Because
no, even before gravity, Waffa-Witten theorem says that the global minimum, the minimum of the vacuum of the energy as a function of theta is around theta equals 0. Of course, it's a periodic function, but
yeah, but you know that in GGD it's not the case because it's cosine theta.
Yeah, but the minimum. It's okay to have absolute. I'm not talking about normalization relative to I'm not talking about relative. I'm saying minimum is that theta equals 0. That's
I would say that cosinus, cosinus theta.
First of all, yes. First of all, Arkady, you know better than me that this cosinus is an approximation, as you know very well. It's a dilute gas approximation, and
right.
About cosinus is that okay? I mean, the only thing we know that it must be a periodic function of theta. And actually, by the way, there are these very, very nice papers by Witten and others that they even contain cusps. Actually, Misha Schiffman had.
He already left. No, but you can find a particular example of theory where you can calculate, kind of when you have cutoff, not gravitational theory, where energy is say would be decreasing as function of theta. This you also can find.
No, but I don't need to find anything. I'm only using Waffa-Witten. I'm only using Waffa-Witten which says that the minimum is that theta equals 0. I'm not even plotting what the potential should be. That's not important for my argument.
I got it. Okay. Thank you, Gia.
Thank you very much.
So Gia, there are other comments and questions in the chat. I think I will probably let Valery Rubakov, who has another question to ask, okay, and then we will free you. Okay.
I mean, you said that there is some kind of a question and answer room or something.
Yes, there is on the web page. There is a place where to ask questions. Okay, and then if you have time, you can reply. But
okay, so
Valery has a question on S matrix. I think it's related to what Akani was asking. So I don't know whether he wants to add anything. So let's see if I.
Yeah. Hi.
Oh, hi, Valery.
I just have a very straightforward question. Why are you so much interested in S matrix? S matrix is never there, right? We all have finite lifetimes, right? So everything happens in finite time intervals. So if you forget about S matrix, what is going to be your argument?
No, that's precisely my point, that you cannot forget about finite. That's precisely my point. That's precisely what I'm trying to say, Valery. Of course, that's again important, but I'm saying that we don't have any other definition of quantum gravity, any other formulation. So now, if tomorrow you will come up with a new formulation of quantum gravity, for example, in string theory, if you find formulation of string theory which doesn't rely on S matrix, for example, I don't know, some new identities or whatever, then of course I go back and reconsider my argument. But my starting point is a fact that the only formulation of quantum gravity.
Well, that's our problem, right? It's not a problem of quantum gravity, because we always have finite time intervals of everything that happens.
Yeah.
Right. So if we don't know how to construct quantum gravity without S matrix, it's our problem. It's not the problem of quantum gravity.
No, that's one point of view. Of course, you can say, and that's a standard point of view. That's you see, Valery, this is very important because I'm trying to change the standard point of view. I'm saying that we naively we would say, okay, maybe tomorrow we'll learn how to introduce quantum gravity without S matrix, or we will learn about approximate S matrix. Okay, maybe. I'm saying no, stop there. You are making a big mistake, because through the S matrix, this poor theory is telling us for I don't know how many years, like I don't know, already 40 or something, that cosmological constant is 0. instead of listening to this theory that tells us the cosmological constant is 0 because theory cannot be defined otherwise on the 0 or negative, because cannot be defined otherwise because it requires arithmetic. Instead, we are ignoring this and we're saying, no, let's ignore this and let's assume that tomorrow there will be some formulation which will allow us to have de Sitter space. And then let's create an artificial problem with de Sitter space and cosmological constant. And let's try to solve it as naturalness problem. That's what you're trying to tell me. I'm saying you should not do that because precisely this is what you should not do. I tried to explain that this thinking that on short time intervals is okay to work with approximate S metrics. And here is the transparency, which discusses that, right? That's a wrong thinking because that assumes that the theory has already been well defined. You have right to do that only if someone told you that theory is well defined. Nobody told you that. Nobody told you that on the Sitter background theory is well defined. So therefore, don't give me these approximate computations on short time scales because they are not correct. By the way, it's obvious that they are not correct. I told you that gravity, if you want to compute scattering of closed strings or gravitons, there is an absolute limit in center of mass energy in which you can use any computation. So simply, you cannot probe distances shorter than a certain distance if you are in the de Sitter space. It's simply impossible because your black hole will become larger than your de Sitter space. Now, you are telling me this is not a problem because tomorrow I may learn how to do this in some other hypothetical theory. Therefore, I should not worry about it. No, I'm saying that's when you learn it, come and talk to me. But before you learn it, I'm telling you that was precisely the mistake. And theory is telling us in every manifestation, this theory is telling us that we were wrong to assume that approximate S matrix works for gravity on the Sitter space. I mean, what else this poor theory can tell us?
Okay.
So that's my point of view. That's precisely the whole point of my talk. That I'm trying to change this standard. Okay, let's call it standard way of thinking. So your question is extremely important because precisely it's exact opposite of what I'm saying. Right.
Okay.
Okay.
Okay. Fantastic. So thanks a lot, Gia, for the talk and 1 hour answering questions. So I think I should thank all the people who asked questions because this created a very interesting discussion. So
well, thank you very much, yes, also for the questions. I mean, including all the questions. I mean, of course, I don't want to create the impression that what Valerie was asking. I mean, I'm disagreeing, but of course, these are absolutely important things.
Yes,
absolutely, yes, and yeah, thank you very much. So these comments will not so they will survive in that section you said.
No, so everything is recorded. So if people want to hear again, they can watch the video. Then there is on the web page there is a Q&A session. I mean, a place where people can ask questions. Okay, and then they will arrive to you, and if you have time, you can answer. Okay.
and also there is room for your slides if you send that to us.
Oh, sure.
So everything is stored in our webpage.
Okay, great. So I'll send it by email. Okay.
Okay.
All right.
Stefania, so do you want to say the final words?
Have a nice summer to all of you, and see you after vacation. I hope everything will be okay in September. Stay tuned on our webpage for the future program. Thank you very much.
Thank you very much. Okay.
Thank you to everybody.
Bye. Bye.
Bye. Bye.
Bye.
Bye.